One of the trickiest aspects of learning about carbohydrates is mastering the ability to convert these chain forms that we have learned of the carbohydrates, which are probably the easiest way to first learn about their structure, to the ring forms. And it turns out that when these carbohydrates are in solution, which is how they normally would be found in a biological system, they are going to prefer to be in their ring forms over their chain forms. The way that we're going to represent these ring forms is as what we're going to call Haworth projections, which are essentially just hexagons that look like they've been squished a little bit on the top. So the way that we're going to go about doing this is that we first number the carbons. So if we're talking about an aldose, the aldehyde carbon is number 1. And if we're talking about a ketose, the carbon is number 2, which has the ketone. Although really we're only going to do this for aldoses for the time being. And then I'm going to ask you to draw what I will call the standard ring template for this. And we're only going to consider 6-membered rings for right now, and we call those pyranoses, although 5-membered rings do definitely exist. So taking what I just talked about in the last slide and showing it for glucose, I've started here by numbering the Fisher projection, which shows the chain form of glucose. And then I've drawn over here what I call my standard template as a Haworth projection. So you see that the Haworth projection here is this hexagon that's kind of been squished. We have oxygen always in the upper right position. And then number 1, 2, 3, 4, 5, and 6. That's how they're always going to be numbered for these D carbohydrates. So let's pay special attention here to a few connections. The most important thing that you need to observe here is carbon number 5, its oxygen is no longer an alcohol. That oxygen is effectively reaching around and bonding with carbon number 1. So this oxygen here is now bonding with carbon number 1. And that is always drawn this way to the right in a Haworth projection. So that is the oxygen of carbon number 5 connecting with carbon number 1. The rest of the work goes into figuring out where the alcohols are going to be positioned. So positions at carbon 5 and 6 are fixed. So once you know the standard template, you don't need to worry about 5 and 6. For carbons 2, 3, and 4, we go back to the chain form and we look at the position of the hydroxyl group. If the hydroxyl group points to the right, then it will point down in the Haworth projection, in the ring. And any hydroxyls which point to the left would then point up in the ring. So let's take a look at how that works. So we haven't dealt with carbon number 1 yet. We've already said 5 and 6 are fine, so we're going to leave them alone. So carbon number 2, if the hydroxyl points to the right, then it should point down on the ring, and that's what we have there. Carbon number 3, this hydroxyl is pointing to the left, so we point it up. And then carbon number 4, any hydroxyl pointing to the right, goes down. And as I said, 5 is always fixed, so if it's drawn to the right here, you'll see it has to be going actually to the right there, because that's a permanent part of the Haworth projection. And then 6 would be always that CH2OH. So let's take a look at a few practical Haworth projections. If we look here, here are some molecules for glucose and fructose. So I just drew the one for glucose, but you'll notice at carbon number 1, we now have a new alcohol. We no longer have an aldehyde. I have chosen to draw that alcohol down, and in a moment you're going to see that it also could have been drawn up. Remember, this carbon used to be an aldehyde, and as we will see, there's no rule saying that that this has to be drawn down or up. It will actually be a mixture of both. I'll get into that in the next slide. Fructose, you'll notice, has a different kind of ring structure. This, instead of being a pyranose, which has 6 members in the ring, so 1, 2, 3, 4, 5, and then that oxygen makes 6, this is going to actually be what we would call a furanose. It is a 5-membered ring. 1, 2, 3, 4, 5. Figuring out furanoses can be a little bit more complicated, and so we are not going to work at trying to figure out how to do the 6-membered rings, and you're not going to need to memorize the structures of the 5-membered rings. We're just going to focus on the 6-membered rings. So it is possible then to get a couple different orientations at carbon number 1. If the hydroxyl group is pointing down, we call that an alpha orientation. That's going to be important, and we'll come back as we'll see when we get into the disaccharides and the polysaccharides. And if the hydroxyl group points up, it is called beta. And so we will find both of these in solutions. Not in equal amounts, it turns out, but we find both of them. And so now, instead of having just D-glucose, we have the 2 forms. So we have alpha D-glucose, which has the hydroxyl drawn pointing down, and we have beta D-glucose, which is exactly the same as alpha, except at carbon number 1, which has the hydroxyl group drawn pointing up. So please remember that. Alpha is drawn down, beta is drawn up. We find that if we look at D-glucose dissolved in water or dissolved in cell solutions, that there is in fact all 3 forms existing. We have an equilibrium. The vast majority of the molecules exist as either alpha D-glucose or beta D-glucose. If we just say D-glucose, that means we could technically have any of these forms. So the chain form cannot have alpha or beta because we don't have an actual position yet on the ring. So again, notice the big difference here. Carbon number 1 is an aldehyde in the chain form, but it is now an alcohol in the ring form. Now we look at another redox reaction. If we take an aldose and add Benedict's reagent, it will be oxidized to an aldonic acid, where an aldonic acid is simply a carboxylic acid. This is just a fancy name to describe a reaction that we have already seen. So, as you might recall from a lab experiment, Benedict's reagent is blue, and that is because of the presence of the copper 2 ion. And when Benedict's reagent reacts with something which it can oxidize, it will reduce to the red copper 1 oxide. So we notice here that none of the groups in carbons 2 down are changed in any way. So Benedict's reagent only targets carbon number 1. So here we are starting with an aldose, which is glucose in this case. It is an aldose because, again, we have an aldehyde. And the aldose is changed into an aldonic acid, which is just a fancy way of saying it is a carbohydrate that's become a carboxylic acid on carbon number 1. When a carbohydrate is able to react with Benedict's reagent, and that would be all of the aldoses, and it turns out ketoses do as well for reasons which we won't go into for right now, all of those compounds are called reducing sugars. And that is because what happens is the aldehyde or the ketone is able to reduce Benedict's reagent. It goes from being copper 2 to copper 1. There are some carbohydrates, though, which are not able to react with Benedict's reagent, and so you will not see any change in the color. And that is largely because the aldehyde groups are not exposed. They are permanently trapped in that ring structure, and such a compound we would call a non-reducing sugar. This provides a good segue into the next topic, which is going to be the disaccharides and the polysaccharides. Monosaccharides can combine to form what we call disaccharides. And many of these are familiar, including perhaps the sugar you use the most, which is sucrose. Sucrose contains, for example, glucose and fructose units bonded together. Lactose is familiar from milk, and lactose contains glucose with galactose. Another one is called maltose, and that contains 2 units of glucose combined together. Now, we can bond these together beyond just 2 to where we'd have, say, 3 together. And when we have 3 monosaccharides combined, that would be called a trisaccharide. And then after a while, we might have a few more, and we get what's called an oligosaccharide, where oligo means few. But rather than going into all those other terms, I'm just going to say that once we get beyond 2, it's common to start calling these structures polysaccharides, meaning many of the carbohydrate units combined. So here is sucrose. We saw this just a moment ago. And if we look at sucrose, you'll see that we have a link here between a glucose molecule and a fructose molecule. We're now going to go ahead and focus on this link that holds the 2 monosaccharides together. So these linkages are called glycosidic linkages. What functional groups best describe what we saw there? So take a look here. So this is a carbon atom to an oxygen atom to a carbon atom. You'll recall that that is considered to be an ether. So we have an ether functional group acting as a glycosidic linkage. We're going to have 2 major types of glycosidic linkages, all based on orientation of the alcohol at carbon number 1. An alpha glycosidic linkage is what we have when carbon number 1 is oriented pointing downwards, and a beta linkage occurs when we have a linkage pointing upwards. So if we go back and look, you'll notice that this oxygen here is pointing downwards. That means the glucose that it came from was alpha D-glucose. So this would be considered an alpha glycosidic linkage. In a moment, we're going to expand beyond that a little bit more as well. Now, when we go ahead and join these sugar molecules together and they form a disaccharide, we ultimately must give off 2 hydrogen atoms and an oxygen atom for them to combine. And so water is a side product when the sugar molecules combine. And we would call this a condensation reaction. Water is produced. On the other hand, we can break up a disaccharide or a polysaccharide into separate units. And when we do that, water is ultimately added into the molecules again. It's restored. And so we would call that a hydrolysis reaction. For example, let's take a look at lactose. In lactose, you'll notice we have here a glycosidic linkage between carbon number 1 of galactose and carbon number 4 of glucose. Here they are, in case you wanted to know where I got those. This is specifically called a beta 1,4 glycosidic linkage. Beta because this oxygen, you'll notice, is pointing up. It comes from an alcohol pointing up. When we go ahead and we hydrolyze this, it forms galactose and it forms glucose. Now, incidentally, to make things easier here, we've drawn this as beta galactose and we've drawn this as beta glucose. But now that they're back in their rings forms, they are not trapped. They can go back to their chain forms and then form the alpha structure as well. But in lactose, we always have a beta glycosidic linkage, specifically what we call a beta 1 to 4 glycosidic linkage. Why is this oxygen pointing down? This is a very important question. Do we call this alpha or beta? No, we don't. Because you'll recall, for glucose, the oxygen at number 4, carbon number 4, always points down. We don't get a choice on what direction the other oxygen groups from the alcohols point. That's already included in the name. Glucose tells us that at carbon number 4, the hydroxyl points down. So this is beta from carbon number 1, 4 to carbon number 4 here. And this reaction, again, is called a hydrolysis reaction. We can specifically look why if we look at all the atoms in detail. First of all, what I'd like to do here is box off all the atoms which we know are not changing in any way at all. And that is going to be, we're seeing here that pretty much everything from here over, nothing is changing here. And similarly, we're not really seeing any changes at all from here to here when we compare with the before and after picture. What you have to look at is this oxygen. This oxygen is now either it's either this oxygen here or it's this oxygen here. We don't really know. And you'll notice also that we've added 2 hydrogens here. So those hydrogens weren't there before. So we have added, as part of this process, H2O. The water is used to break the glycosidic linkage, hence a hydrolysis reaction. Focusing on lactose for a moment, normally we are able to break down glucose and galactose using an enzyme which occurs within us called lactase in the digestion process. Now, there are many individuals who do not have an adequate amount of that enzyme within their bodies for whatever reason, and they are considered to be lactose intolerant. What this means is that there is now technically a competition within your body. These people who don't have adequate lactase, they are breaking up the lactose, but the problem also is that bacteria within their digestive tract also starts to break up the lactose. And while your body is able to break up lactose without any side effects, when bacteria break it up, they also give off gas during that process. And that is what ultimately causes the discomfort and bloating which is associated with lactose intolerance. Beans contain a trisaccharide called raffinose. Trisaccharide meaning 3 monosaccharide units joined together. And humans do not have the enzyme that they need to break up raffinose. However, just like with the case of lactose intolerance, there are bacteria within the intestines that are able to break down raffinose. And we run into a similar problem in that those bacteria give off gas. So beans are generally associated with flatulence, which is, of course, a polite way of saying farting, and that all derives from the breakdown of that trisaccharide raffinose, which we lack the enzyme to produce. There is a product commercially available called Beano, which essentially temporarily gives us access to that enzyme and facilitates breaking down raffinose before the bacteria in the gut get a hold of it and start producing gas. So moving beyond units of 2, we're going to move to many units of sugars. And so technically poly means many, and that could mean 2, 3, 4 carbohydrates, but usually when we're talking about polysaccharides, we're talking about molecules that contain hundreds to thousands of the monosaccharide units combined. Now, they can combine together in different patterns, and owing to those different patterns, we get different properties. And when I'm talking about different patterns, I'm specifically going to be referring to the glycosidic linkages, whether they are alpha linkages or beta linkages, and also whether they are always linkages between carbon number 1 and carbon number 4, or if they are between other atoms. So I'm sure you're all familiar with the compound starch, which is a common part of most of our diets. And starch is a polysaccharide of many, many D-glucose molecules. Incidentally, I'm not going to always say D-glucose, but unless I say otherwise, the D is implied from here on out. And the D-glucose molecules are joined together by alpha linkages. So we have many, many glucose molecules all joined with alpha linkages here. If, on the other hand, we have beta linkages between the different glucose units, we get a molecule with an entirely different set of properties called cellulose. So we'll focus first on starch, and then we'll look at cellulose a little bit later. But suffice it to say, starch is going to primarily be found in a cyclic, twisted kind of structure called a helix, whereas cellulose, owing only to the differences between the linkages, forms long chains. So here we have on the top alpha glucose, and what we're trying to show here is that we're combining various glucose units. So here we have a glucose unit bonded to another glucose unit, and as these get longer and longer here, you'll notice that these alpha linkages ultimately form a helix, a twisted shape. So it is alpha, again, because of the position of the hydroxyl on carbon number 1. However, if we go ahead and we look at cellulose, the hydroxyl group is oriented up. That is the beta position. Now notice on carbon number 4, the hydroxyl in glucose is always down. As I said earlier, that's fixed for glucose. It's always down for glucose. So the only one that can change is the hydroxyl at carbon number 1. So if the hydroxyl is beta, it will join and it will ultimately form a long linear type of a structure. So starch can be found in a couple forms when we're first taking it into our diet, and the first is amylose. So amylose consists, like pretty much all types of starch, as long coiling helixes. And then we have amylopectin, which also consists of helixes, but with one important difference, and that is that there is a much greater amount of what we call branching. So whereas we will have helixes with 1 to 4 glycosidic linkages, there will be many more other linkages in addition to 1-4 linkages to cause branching. When we consume starch, and we get a mix again of amylose and amylopectin, the body ultimately stores this for short-term use as glycogen. And glycogen is very similar in structure to amylopectin. So, for example, here, if we look at potatoes, and potatoes have these accumulations of starch within their cells, we see that we have a mix in that starch. About 20% of it is amylose, for which we see very little branching. And in fact, this picture shows no branching at all in the polysaccharide. On the other hand, with amylopectin, if you follow right here, let me go ahead and highlight. If we look right here, there's kind of a main helix going on right there. Okay, so we see that helix right here. But you'll see there's several branches. So for example, right here we have a branch, and right here we have a branch, and other branches as well breaking off of the main helix. And these are not at 1,4. For example, this would be at carbon number 2 if we look at it on the picture. And then here this looks to be carbon number 3 if we look at the picture. Although it's hard to tell exactly from the picture itself. So there are many branch points within amylopectin. Now, if we were to look at glycogen, which is how starch is ultimately stored in the body, you'll notice that there are indeed still branches, which make this structure similar to amylopectin, although if we looked at the exact details, we would see that there is some differences within the branching. Here we have an example of some muscle tissue which has been stained to make the glycogen stand out. And in the next picture we can see this even more prominently, where we have lots of these little purple spots sticking out. And so what we have here are many, many glycogen granules being stored, in this case, within liver cells. So muscle tissue, liver tissue, those are all types of cells in which there's going to need to be a lot of energy expenditure, and so we would expect glycogen to be found in such locations. Cellulose is the other important polysaccharide which is made up of glucose units. Cellulose is the most abundant organic compound on Earth because it is found in plant cell walls, and with there being a huge number of plants on the Earth, it would only make sense that there would be a vast amount of cellulose within them. While we rely on starch as an important nutritional food source, cellulose absolutely cannot be a source of energy, despite the fact that it's made up of many glucose units. And that is because we simply lack any enzymes which would be able to break down the glycosidic linkages. So the alpha glycosidic linkages in starch, specifically alpha 1 to 4 glycosidic linkages, we can break down, but we cannot break down beta glycosidic linkages. However, when we consume plant material, cellulose does play an important role. It acts as roughage, which is good for essentially cleaning out the digestive tract. And if we look throughout nature, we find other carbohydrates which also provide support to cells or provide a structural element. Perhaps the most important of these is chitin, which is found, for example, in the shells of insects and crustaceans. So, as mentioned, we find cellulose in plant cell walls. And so if we go ahead here and look at a microscopic picture of a cell wall, we see this long series of fibers. And those fibers are essentially bundles of the polysaccharide cellulose. And the cellulose strands line up and are held together by hydrogen bonds, giving them even greater strength. Now, carbohydrates play an important role in the diet. The primary role when we look at carbohydrates, particularly monosaccharides, things like glucose, is to provide an immediate energy source. For example, the brain demands a vast amount of glucose to keep running from hour to hour. Excess carbohydrates can be shifted off to two different uses. They can either be used for short-term storage, in which case they are converted to glycogen. We saw pictures of glycogen just a moment ago. And eventually it can also be shifted over into long-term storage as fat. So those are essentially our three uses here of glucose. It is either broken down immediately to give off energy, stored short-term as glycogen, which has a starch-like structure, or it's ultimately converted into lipids, which will be the focus of the next chapter. Carbohydrates play other important roles physiologically as well. For example, carbohydrate chains that are found on the outsides of red blood cells are used to differentiate blood types. We have 4 distinct types of chains of carbohydrates that can be found, and they essentially are unique to each one of the blood types. And we have 4 different blood types here. They're the O, kind of called the universal blood type, A, B, and AB. There are also positives and negatives, but I'm not going to get into those right now. So imagine, if you will, that we have here the surface of a red blood cell. Now, no one red blood cell could have all of these different chains here, but if we had someone who had O-type blood, that person would have this series of carbohydrates coming out of the red blood cell. And these would be a combination of glucose, glycosidically linked to galactose, which is linked to N-acetylgalactosamine, the N indicating that there's a nitrogen in that particular carbohydrate, to another galactose, and then to a fucose, which we did not talk about. Now, I want you to compare O blood types to the other three blood types. You'll notice that it is exactly the same sequence of carbohydrates up to that point. So with a B blood type, it's the same as O, but with a galactose coming off of the end galactose, as it were. And then there is an N-acetylgalactosamine for the A blood type. And then there's quite a bit more branching for the AB blood type. So we see here that that is an important role in differentiating between these. And it's important that when a patient be given blood, that they be given a blood type which is compatible for them. If there are incorrect or non-compatible blood types given to someone in the midst of a transfusion, the problem is that the immune system of that person will consider the blood cells to be invaders and attack the cells or go into an immune response, which causes other problems. So ultimately, it's the carbohydrates which designate blood types. This brings us to the end of Chapter 14. We continue our look at biomolecules with Chapter 15 when we get into lipids.